Okay, so in a linked list, you store the data as a node, and they are not necessarily going to be in consecutive blocks of memory. So you're going to have the data spread out throughout the memory. So this alleviates the need as you have an array uh, that you need consecutive blocks of memory. But the kind of the other side of this is, since the data is kind of distributed throughout the memory, you need to be able to keep track of where the next element is. For example, if you have a list of elements with data say 20, 45, 12 and 17, I need to know after 20 where is the next element in the list. So in order to keep track of this, you need to store what is called the address of each node. So that's why you package the data as well as the address of the next data node as a node. Okay. So if in this case the list is 20, 45, 12 and 17, you cannot just store this. You have to have the address of the next data element, which we call as a node. Okay. All right. So basically you have two type of linked lists: the single linked list and double linked list. So in a single linked list, you can traverse only in the forward direction, basically in one direction, whereas in double linked list you can traverse in both directions. Okay, so in the case of a single linked list, you have what is called a head node that that does not have any data element in it, or basically its data member variable is kind of not set up. Um, Before that, let us see what is the structure of a node. So a node consists of the data and the address of the next node. Okay, so for the head node, the data is not set up. It stores the address of the first data node. So in this example, the first data node is at address 120. So that is where the first data node is. So here you see the data, which is 20, and the address of the next data node, which is 136. So you go to address 136, there you have the data 45, and the address of the next data node, which is 156. So you have the data 12, and the address of the next data node is 176, which is here. So the data is 17, and the address of the next data node is null set to be null. So that means this is the last node, last data node. So in this setup, you can traverse the linked list in the forward direction, starting from the head node all the way up to the last data node. So as you can see, so a node object should have the data and the address of the next data node. Okay. Now, in the case of a double linked list, you can traverse the list in both directions. So you have, say, again, a node has three elements now. So the data, as well as the address of the next node, as well as the address of the node previous to this node. So you can traverse in the forward as well as in the reverse direction. Okay, so let us look at the forward direction. So in the case of forward direction, you start from the head node and don't have the data set up for this head node as before for a single linked list. Now among the three elements, only the next node address is set up, which is 116. So the previous node address is also not set up. So 116 is the address of the next data node, which is the first data node. So that's the data here. So looking only at the forward direction, so the next node is at address 132, and the data is 45. The next node is at 152. The data is 12. Next is at 172. Data is 17. Now that next node address is set to null, so that means there's no. This is the last data node. So start from the head node and you can traverse the forward direction until the last data node. Now in the reverse direction, you start from the tail node, and here for the tail node, the data is not set up, the next node address is not set up, but the previous node address is set up, which is 172. So that means from the tail node you can go to the, so this is the first data node in the reverse direction. So the previous node address is 152. Then you can go to this node. The previous node address is 132. You can go to this node 116, and the previous node address is 0. So that means there's no node previous to this node. So from the tail node you can traverse the list in the reverse direction. Okay. So as you can see, in the case of a double linked list, a node should have an integer, in general the data, as well as the next node address and the previous node address. Now if you look at the memory consumption point of view, if each integer is storing 4 bytes, the address of a node is also 4 bytes. That's what memory address we are assuming in this course, that memory address takes up 4 bytes to store. So a node in a single linked list will take up 8 bytes of memory, and a node in a double linked list will take up 12 bytes of memory, because 4 bytes for the integer data, 4 bytes for the next node address, and 4 bytes for the previous node address. Okay, so let us, in this module, we'll focus on the implementation using a single linked list for a list ADT. So the node class will have two member variables, as we just saw in the figure: the data, which is an integer in our implementation, the examples, and then the next node pointer stores the address of the next data node. The node constructor is an empty constructor because we use the set and get functions, set functions to set the member variables. So set data, then the set next node pointer. Now this is a pointer, so you need to pass the address. So capture through this pointer variable node ptr. So next node ptr can be now set to node ptr. Then you have the get functions for the data and the next node address, which is a pointer, so it should return node star pointer data type. Okay. All right. So again, we saw something like this in the earlier example too. So let us look at the constructor for the list class. So you saw this is a node class. So for the list class, we need to only store the address of the head node. So as long as we store the address of the head node, we can traverse the entire list in the forward direction. So for example, if I store the address of the head node is at address 100. So where do we store the address of the head node? In a pointer called head pointer. So head pointer stores the address of the head node. So if you look at the list class, the only member variable you have is a head pointer. It stores the address of the head node. So in this example it is 100. So once you know the address of the head node, you can access the head node. Once you get to the head node, you can get the next node pointer address using the get next node pointer address on the node in the node object. So that will be 200. So you can go to this address, access the data, get the next node at address 70. Data is 5, next node is at address 500, and so on. As you can see, the data is not in consecutive blocks of memory. The memory addresses need not be like in the increasing or decreasing order. They could be in any arbitrary order. Okay. So how you set up the list object initially in the constructor, you can see like the list is empty. We have not yet set up the data. So the head node is only node now in the list. So we're just creating the head node. So new node is going to create the node, and we are assigning the address of that node to the head pointer. So the head pointer stores the address of this node. So we call this the head node, and we say head pointer arrow set next node pointer is null. So this is how it is set up. See, we don't even need to set up the data to be null or some meanwhile value. There's no need to worry about it. Just set the next node pointer address for the next for the head node to be null. So now let us look at how to insert a data to a linked list, to a single linked list. Okay. So in order to do this, well, let us go to an example and then we'll come back and look at this code. So let us say currently the list is this, has elements 10, 5, 7, 9, and you want to insert one more element to this list. at the end of this list. So let us say we want to insert 30 at the end of this list. So after insertion, the list should be like 10, 5, 7, 9, and 30. Alright, so this is how the list is. So the head pointer stores the address of the head node, and from there we can traverse through the list. Now we maintain two pointers, and this is a logic that we'll use several times in this course. So the two pointers are like this, they'll follow one after the other. So we'll call something as the current node pointer. So that pointer will store the address of the node that we are currently looking at. And there is something called the previous node pointer that will store the address of the node previous to the current node. So initially the current node pointer will be set up to be storing the address of the node next to the head node. So we say head pointer arrow get next node pointer. So head pointer is pointing the head node because it stores the address of the head node. And when I say head pointer arrow get next node pointer, I'm going to get the address of the node next to the head node. So that is 200. So current node pointer will be 200. So using the current node pointer, we can basically access this node. Then the previous node pointer is initially set up to take the value of the head pointer, which is 100. So the previous node pointer is also pointing to the head node, like the head pointer. So now what we do is we move through the list one node at a time. So how do we move through the list? So we move through the list until the current node pointer is not null. So this is how we move through the list. So the first thing we do is set the previous node pointer to take the value of current node pointer. So previous node pointer will take the value of current node pointer, which is 200. So previous node pointer as well as the current node pointer will point to this current node. And then current node pointer takes the address of the node next to the current node. So current node pointer arrow get next node pointer is 70. So that will be the value of the current node pointer after the second statement. And this is what we do repeatedly inside the loop. Then the previous node pointer takes the value of current node pointer, which is 70, and the current node pointer takes the value of current node's next node pointer, which is 500. And we do that repeatedly until what happens is, now you see the current node pointer is pointing to this node and the previous node pointer is pointing to this. So now previous node pointer will get the value of current node pointer, which is 700, and then current node pointer will get the next node address for this current node, which is 0. So current node pointer becomes null, and in the next iteration you come out of the loop. Then after you come out of the loop, see, until now we have not yet inserted the data. So notice that when you come out of the loop, the previous node pointer is storing 700. That's the address of the last data node. So after you come out of the while loop, you have to really now set up the new node. So we say new node pointer equals new node of. That means you're creating the new node and assigning its address to new node pointer. And you say new node pointer arrow set data is 30, and then you can set the next node pointer for the new node to be null. That's because there's no node data node following this node, because this is going to be the last data node in the list. And now we have to still link it up. So previous node's next node pointer should be set to new node pointer. So previous node pointer arrow set next node pointer can be set to the new node pointer, which is 900. So now the last data node before this insertion is now linked to this new data node. So we almost went through the code. So if you look at this, insert data. So current node pointer initially stores the address of the node next to the head node. So head pointer arrow get next node pointer. And the previous node pointer stores the address of the head node, so it's equal to head pointer. Then loop through the list by moving the current node pointer and the previous node pointer. So initially the previous node pointer is taking the value of current node pointer so that you can have a handle on the current node, and then move the current node pointer to point to the next data node. And then this is how you set up the new node. First, create the node, assign its address to the new node pointer variable using that new node pointer. Now you can set the data as well as the next node address is set to null, and then link the previous node to this new node. So previous node pointer arrow set next node pointer will be this new node pointer. Now, if you want to write a function, say is empty, so that means you want to check if the list is empty, then all you have to do is look at see how we set up the empty list. So head pointer arrow get next node pointer, if it is null, you can return true, because the head node's next node pointer will be null, otherwise return false. Okay. Now, using a similar logic, we can also insert at a specific index in the list. So a very similar idea. The only thing additional you have to have is you have to keep track of which node we are currently looking at and where you want to insert. Now, even though we don't have an explicit index for the list, we can still say I want to insert at index 2 or index 3 and so on. So let us use this example. So let us say you have this list 10, 5, 7, 9, and so 10 is the first data node, so we say it's at index 0. 5 is the second data node, let us say it is at index 1, and then 7 is the third data node at index 2 and so on. Now we want to insert this element 30 at insert index 2. So that means after insertion the list should be like 10, 5 at index 2 should have 30, and then 7 will be 9 at index 3, and then 9 at index 4. Okay, so this is the list currently we have 10, 5, 7, 9. So after insertion we would like to have 10, 5, 30, 7 and 9. Okay, so that's what we want to accomplish. Alright, so again as before we set up the previous node pointer and the current node pointer. Point to the previous node pointer is pointing to the head node, and current node pointer is pointing to the node next to the head node. Now we will use a kind of temporary or dummy variable called index to keep track of which node we are currently looking at. So index always takes the value corresponding to the current node we are looking at. So in current node pointer is pointing to the current node, which is the first data node, so index will be set up to 0. And then the idea is inside the while loop, as we move the pointers, so first set the previous node pointer as before to the current node pointer, and then move the current node pointer to take the value of the next node and to the current node, the address of the next node to the current node, and do index plus plus. Okay, so when current node pointer is pointing to the second data node, which is index 1, it matches with this, so index is set to 1. So keep doing this until the value of index becomes equal to insert index. So when the value of index becomes equal to insert index, that's the time we have to do the insertion. So we create the new node, set its data, and then what we do is now we have to do two things. So currently previous node pointer is pointing to 70, current node pointer is pointing to the node at index 2, so current node pointer is 500. So you want to insert this 30 in between this 5 and 7. Okay. Alright, so after you set up the new node, and new node pointer address is 900. Now using the previous node, or we can do this. So new node next node pointer can be set to the current value of current node pointer. So new node pointer arrow set next node pointer will take up the value of this current node pointer. Then the previous node pointer arrow set next node pointer will take up the value of this new node pointer, so that the link is set up from the previous node to the new node, and from the new node to the current node. So let us look at the code. So insert at index, so we just saw all these things. So set up the previous node pointer to point the head node, current node pointer to point the node next to the head node, index is set to initialize to 0, and move through the list until the current node pointer is empty. You can break earlier. So when do we break? If index equal to insert index, we break from the loop. If you don't have, should not break up, from the loop, break out of the loop, then we simply move to the 2 pointers, previous node pointer and the current node pointer, or move to the next one node at a time. So and then we do index plus plus. So then once we come out of the loop, we set the new node, and the new node pointer stores the address of the new node, and the new node pointer set data to be the data that we want to have, like in this case 30, and the new node's next node pointer is set to the current node pointer. So the node next to the new node pointer is going to be now the current node that we are looking at, and the previous node's next node pointer is set to the new node pointer. Now, using a similar logic, we can write the read function where you want to read a value at a specific index. So exactly the same logic, but the only difference is if index equals to a read index, just return the data of the current node. Current node pointer arrow get data will return the data of that current node. Now modify element is the same logic. If index equals modify index, current node pointer arrow set data, you can set the data whatever you want and then return from this function. Okay, so the next critical thing that we have to look at is the index delete function. So let me stop this video for a moment. Well, okay, continue. Alright, so let us look at the delete function for a linked list. So let us use an example again. So let us say we have 10, 5, 37 and 9. Again, 10 is at index 0, 5 is at index 1, 30 is at index 2 and so on. So we want to delete the element at index 2. So after the deletion, the list should be 10, 5, 7 and 9. Okay, so the way we do that is we use again 2 pointers, previous node pointer and current node pointer. We also use one more pointer called the next node pointer. Now the previous node pointer and next node pointer are initially set up to point to the head node, so they take up the value of the head pointer, and the current node pointer as usual takes up the address of the node next to the head node, so that is the first data node. So that is 200, and index is set up to 0, and we move through the list until index equals delete index. So the first case index is 1. So index is 0, so we move the previous node pointer to take a value of current node pointer, so it's 200, and the current node pointer moves to the next node, which is 70. Okay, and then keep moving, so index becomes 2, so current node pointer is pointing to this third data node at index 2, and previous node pointer is pointing to the node before that. Now this is the time what we have to do is we have to kind of isolate this node because we want to kind of delete it, but we don't want to totally remove this sort of memory. We want to kind of logically isolate this data node. So the way we do that is store in the next node pointer that we were currently pointing to the head node, store in it the address of the node next to the current node. So after this node, what's the next data node? Where is it? So from using the current node pointer, we can get the address of the next data node, which is 500. So set the next node pointer to be 500, so that means it's pointing to the node next to the current node. So once we do that, what we have to do is set the address of the next node pointer in the previous node to the address of the node next to the current node. So that means previous node pointer arrow set next node pointer will be the next node pointer value, which is 500. So that way you're kind of breaking this link. So from 10, 5 you will go to 7, 9. Now this link will be still there, but we cannot get to this data node. So there's no use of this link to go from this node to this node because we cannot get to this node first of all. Okay, so this is how we delete a node. So let us look at the code. So we set the current node pointer to the address of the node next to the head node, and the previous node pointer and next node pointer are set to head pointer, so they take up the value of the head pointer. That means they're pointing to the head node. Index is initialized to 0. Now you loop through the list as usual by checking current node pointer is null or not. Now if index equals delete index, we have reached a node where we want to delete, so set the value of the next node pointer to be the next node pointer of the current node pointer and break from this list, and then set previous node's next node pointer to be the next value of next node pointer. Otherwise just move through the list and also keep incrementing the index. Okay. Alright, so when it comes to time complexity, which one you would prefer for what? So with a dynamic array based implementation, we can access any element in the array in constant time. So that means we can read or even modify any element in constant time, any index in constant time. Whereas in a single linked list or even a double linked list, you have to traverse to the list. You cannot just go to that particular index. You have to start from the head node and visit one node at a time, and then go to that node that we want to read or insert, whatever operation we have to do. Similarly, insertion in an array is also expensive because as we saw the shifting that was required, and deletion is also expensive. So insertion and deletion, all the three will take big O of n time. And counting, of course, with an array using the end of array variable, you can count the number of elements. As a single or double linked list, it's big O of n. You have to scan through the array. You can set it of n too. You can check the isEmpty function just in the case of a linked list, whether the head node's next node pointer is null or not. In the case of an array, you check end of array is -1 or not. Okay, so which means we can conclude that we will use an array, a dynamic array based implementation, if your the list ADT requires more read operation. On the other hand, if your list ADT requires more write operations, or which means insertion or even deletion, then you would go for a single linked list. The reason, again, as I said, is if you keep inserting, that means probably list size will grow. So to save memory, you would prefer a single linked list rather than a dynamic array. As well as in the dynamic array, you have to do this resizing operation every now and then as you double the size of the array. The single linked list insertion is just one pass through the list and then insert the new data, that node that we want to insert. You can even insert in them somewhere earlier at a specific index using the same logic of traversing through the list. So that's why we say it's big O of n. So if your list ADT requires more insertion or deletion operations, then a single linked list based implementation will be preferable. Okay, so I'll stop with this.